Hi and welcome to John's Maths book. In this video, we're going to be looking at complex numbers. If you like the video, then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. So what is a complex number? What would happen if we had the square root of a negative number, let's say the square root of -4? In normal circumstances, we'd ask what number, when multiplied by itself, gives us -4. The answer is there's not a number when multiplied by itself that will give us -4. So how do we manage this in mathematics? Well, we use the letter I and we let I equal the square root of -1. If we now consider that -4 is 4 multiplied by -1, we have the square root of -4 is equal to 4 multiplied by -1. Simplifying this, we have the square root of -4 is equal to the square root of 4 multiplied by the square root of -1. If we now substitute I for the square root of -1, we have the square root of -4 is equal to the square root of 4 multiplied by I. And using the positive square root of 4, we have the square root of -4 is equal to 2i, which is our final answer. Let's take a look at another one. Let's suppose we want to find the square root of -25. Now the square root of -25 can be written as the square root of 25 multiplied by -1. If we simplify this further, the square root of -25 is equal to the square root of 25 multiplied by the square root of -1. If we now substitute I in for the square root of -1, we have the square root of -25 is equal to the square root of 25 multiplied by I. And taking the positive square root of 25, we have the square root of -25 is equal to 5i, which is our final answer. Let's look at one more of these. Let's see if we can find the square root of -7. So we can rewrite the square root of -7 as the square root of 7 multiplied by -1. Simplifying this, the square root of -7 is equal to the square root of 7 multiplied by the square root of -1. Substituting I in for the square root of -1, we have the square root of -7 is equal to the square root of 7 multiplied by I. And therefore, the square root of -7 is equal to the square root of 7i, which is our final answer. Let's now take a look at how these techniques can be used to solve quadratic equations. Let's try and find the roots of the quadratic equation 2x squared minus 6x plus 5 equals 0. We'd normally expect our quadratic to have two roots. That's where the parabola shape it makes crosses the x-axis. Let's plot the graph of this and see if it's true. So this is the graph of the quadratic 2x squared minus 6x plus 5. As we can see from the graph, it doesn't cross the x-axis and appears to have no roots. So what's going on here? Let's try and find the roots of our quadratic equation. So our quadratic equation 2x squared minus 6x plus 5 is equal to 0 is in the form of ax squared plus bx plus c equals 0. We can use the quadratic formula to try and find the roots. So the formula is minus b plus or minus the square root of b squared minus 4ac divided by 2a. Substituting in for a, b and c, we have 6 plus or minus the square root of 36 minus 4 multiplied by 2 multiplied by 5, all divided by 2 multiplied by 2. Simplifying this, we have 6 plus or minus the square root of 36 minus 40 divided by 4, which gives 6 plus or minus the square root of minus 4 divided by 4. Noting that minus 4 is the same as 4 multiplied by minus 1, we have 6 plus or minus the square root of 4 multiplied by minus 1 and all divided by 4. If we now substitute I for the square root of minus 1, we have 6 plus or minus the square root of 4 multiplied by I, all divided by 4. And simplifying this, we get 3 over 2 plus or minus a half multiplied by I. We now have two numbers of the form a plus bi. These are called complex numbers, as they have a real part a and an imaginary part b. Using our two complex numbers, both have a real part of 3 over 2. In the first number, the imaginary part is a half, and in the second number, the imaginary part is minus a half. These are called complex conjugates, as the real part is the same in both numbers and the imaginary part is equal in magnitude but opposite in sign. In quadratic equations with real coefficients, complex roots always appear in conjugate pairs. We can plot complex numbers on an Argand diagram. The x-axis represents the real part of the complex number, and the y-axis represents the imaginary part of the complex number.